Hi, everybody. Sorry I can't be here today, but we're moving into the unit on forces. Forces are one of the most common aspects of physics. Forces are just a pull or a push. But before we get into forces, I need to talk about Galileo's thought experiment. Up to this point, until Galileo's time, everybody sort of followed Aristotle. Aristotle's ideas were the idea that every object returned to its natural state. A bigger rock fell faster than a smaller rock because, of course, the bigger rock had more earth in it and therefore wanted to return to the earth more than the small rock. The other thing Aristotle stated was that the natural state of every object was to be at rest. And Galileo said, well, wait a second, is that always true? And Galileo, we're talking before the time of modern clocks or any measuring devices, was working with balls on ramps. And one thing he discovered was that if you roll a ball down a ramp, it gained speed on the way down, and on the way back up again, it would lose speed until it got to the point where it would get back to the original height, at least pretty doggone close. The interesting thing about this was the fact that if you put down a shallower ramp over here, the ball would have to roll further before it would get back to the original height. And Galileo said, well, wait a second. Hmm, what would happen if you put an even shallower ramp? Well, in this case, if you put a much shallower ramp, one that went over like this, the ball would roll even further. It would have to go all the way over to here before it would get back to its original height. And if you put one over here, it would roll even further before it got back to its original height. And then Galileo, being Galileo, said, well, wait a second. What if you didn't put a ramp on the other side? How far would the ball continue to roll before it got back up to the same height? And the answer, of course, would be is that officially it would never get back to its same height. The ball would roll forever. And at that point, Galileo said, wait a second. Perhaps the natural state of an object is to remain in motion unless it's acted upon by a net external force. And this was a radical departure away from Aristotle, who stated things naturally come back to rest. Galileo said, you know what? I think actually the natural state of things are to stay in motion unless friction or some other force stops them. And it turns out Galileo was absolutely right about this. And that leads us into what Newton eventually came up with his first law. An object in motion stays in motion, object rest remains at rest unless acted upon by a net external force. But talking about these forces, we first have to identify them. And so, as I mentioned before, a force is defined as a push or a pull. And there's four very simple forces that affect most of our daily life. Force of friction, which we're going to write as F sub g. The normal force, we talked about this briefly before, F sub n. Tension, and the force of friction. As you see in the bottom of the slide, there's many other forces. Magnetic forces, electrostatic forces, lift forces, buoyant forces, nuclear forces. But the four listed above are the ones that you experience most commonly in everyday life. And we're going to talk about these four a little bit today, and we're going to work with them on the worksheets tonight. So real quick on this one before we get going, the unit of force are named after Sir Isaac Newton and are simply called newtons, and are abbreviated as capital N. If you're curious, the imperial unit of force is the pound. That's our unit of force in the U.S., which is a little strange. The unit of mass, of course, is the kilogram in the metric unit. And if I haven't mentioned before, I know I told some of you this because it's a little bit bizarre. The unit of mass in the imperial system or the American system is the slug, which no one uses. Everybody talks about pounds, but technically pounds are the force of gravity on an object, which we sort of use as our mass unit, which is really bizarre. But kilograms, unit of mass, force measured in newtons. In the imperial system, the unit of mass is the slug, and the unit of force is the pound. Real quick, how do we figure out the force of gravity since we're talking about it? If you take a simple spring scale, which is designed to measure force, and hang different masses on it, you'll discover that you end up with a beautiful graph. You can see my Excel graph right here, where the force is equal to the mass times 9.81 newtons per meter, which would be the slope for this thing. Units, of course, being newtons over meters, or sorry, newtons over kilograms. I'm so sorry saying that. And you might say, wait a second, that sounds really familiar. Yeah, it turns out that unit right there is the acceleration of gravity. And so you can write gravity either as 9.81 meters per second, or you can also write it as 9.81 newtons per kilogram. It turns out those two units are equivalent. And College Board actually likes it, or likes thinking about it as so many newtons per kilogram. Fields and gravitational fields are one of those. Sorry, I have a problem writing my kilogram here. Fields are always written or expressed as a certain amount of force per unit something. Gravitational fields are force per unit mass, newtons per kilogram. And so they usually like writing gravity as 9.81 newtons per kilogram instead of 9.81 meters per second squared, the acceleration of things falling. Both of them are equivalent and they're both the same, but it turns out to figure out the force of gravity, it's pretty straightforward. You just need to take your mass in kilograms times the acceleration of gravity. Either is 9.81 newtons per kilogram or 9.81 meters per second squared, and it gives us the force of gravity acting on it in newtons. Real quick on this one, yeah, so you'll see this written this way, the shortcut form, mass in kilograms times the gravitational field, 9.81 newtons per kilogram squared, or sorry, newtons per kilogram or meters per second squared. And gravity, just quick remind or mention on this one, always points towards the center of the Earth, no matter where you are. And here's one that people are always, I guess after projectile motion, you're probably clear on this one. The force of gravity is not affected by the motion of an object. No matter how fast you're moving or what direction you're going, the force of gravity is always the same. It's your mass in kilograms times 9.81. That's it. And it's always pointing directly towards the center of the planet, no matter where you're at. That's it. It's very, very simple. Just a real quick example problem. If you have a 50 kilogram person, I'm going to draw them standing over here on the ground, the force of gravity on them would simply be 50 times 9.8, or 490 newtons acting downward. And we're always going to draw in this chapter force vectors as fat vectors. In other words, instead of just simple lines, as sort of wide arrow vectors like this, just to distinguish them between our, for example, a velocity vector or an acceleration vector, which we always made as simple lines, just to distinguish that this is something different. Force is a vector quantity, so it always has a direction, and in this case, gravity always direct towards the center of the planet. All right, normal force. We've mentioned this one before. We usually write it as F sub n, is always acting perpendicular to a surface. So in this case over here, you see this person pushing on a wall. She's applying a force this way, and the wall is applying a force backwards. Even though she's sort of aimed this way, the force is always perpendicular to the surface at every single point of contact. Yes, there's also normal force on this hand here. I just didn't want to draw it because it gets a little bit messy. It's equal to the force that the surface must provide to prevent an object from passing through the surface. And we've talked about this before. It's primarily through electron-electron repulsion, but even more importantly, the Pauli exclusion principle, that no two electrons with the same four quantum numbers, n, m, l, and s, can occupy the same space at the same time, which is why you can't put your hand through your tabletop. And again, quick reminder, what causes the normal force? Everything you see around you is a spring. If you remember, when you apply or place an object on a spring, it will compress, and it'll compress until the point where the force of gravity on the object is equal to the normal force that the spring is applying upward. If you put a heavier object on it, the spring will compress more, and at that point, the force that the spring provides again will match the force of gravity. The same thing happens when you stand on a floor. When you walk on this floor, it literally bends when you're wherever the place you're standing. And what happens is the normal force exerted upward by the floor is equal to the force of gravity on the thing that you place on the floor at that point. And yes, I've overemphasized it here, but I can literally prove to you that the floor and everything around you bends when you put things on it. Your tabletop bends downward when you put your laptop on it, or your iPad, or your books, or your backpack, and the floor really does bend when you step on it. It seems so strange, but it really does. The bigger person would make the floor bend even more until the point where it would equal, that's me standing on the floor compared to any of you, it would deflect more. And again, just like a spring being compressed, the more you compress it, the greater the upward force it exerts on that object. Tension's the third force. So we've done force of gravity, which is just mass times acceleration of gravity. We've done normal force, which is the force exerted by an object to prevent an object from passing through it, always perpendicular. And then tension. Tension is inside of a cord, string, chain, support, or wire. And that's always equal, and this is critical. Tension is always equal throughout the entire length of the cable, and equal to the tension exerted on each end of the cable. Tension always acts in a direction perpendicular along the cable. Parallel, not perpendicular. I'm making all these mistakes. So in this case, in a tug-of-war game, the tension here is acting here and here. We've got two teams. This team's winning. Let's say this team's actually going backwards. This team's falling forward. What's true about the tension on the left compared to the tension on the right? The answer is, well, you're like, wait, this team's winning. This team's pulling backwards. This force here must be larger than this force here. The answer is no, that's not the way the tension works. In this case, the tension on the left is exactly equal to the tension on the right. And you're like, wait, how could the one team be winning if these two tensions are always equal? Remember, the tensions are always the same throughout a rope. How is this team winning? The answer is these are not the only forces acting on these two teams. This team has a greater force of friction between their feet. We'll talk about friction in just a second. Than this team does acting this way. And because of that, both of these systems, if you look at this one, the force friction is larger than this tension, so this person's accelerating this way. And this person, the tension is larger than the force of friction, they're accelerating this way. So how do you win a tug of war? It's not just strength and angle, it's also the friction between your feet and the ground. Believe it or not. So take a look at these situations. Real quick on this one, or on these, let me see if I put this in here or not. Nope. The force of gravity on each one of these 1 kilogram masses is going to be 1 times 9.8, or 9.8 newtons. I'm going to draw it on here real quick. So what does the tension in this cable have to be? The tension here would have to be 9.8 newtons. And pulling down on the top here, remember the tensions are the same for each one of these. This rope or cable will be pulling down on the ceiling with 9.8 newtons as well. The question is, what's the tension there at this point right here then? It turns out the tension there is the same as every other point. And this one's hard to believe, but believe it or not, the tension in the middle here would be literally 9.8 newtons. You're like, wait, how could you actually measure that? You could, at this point, take this same string, cut it, put a spring scale, like the thing I had on the other slide, sort of like the thing you would use to weigh fish, but calibrate in newtons, and tie that mass on here. And believe it or not, that would still read, this is a 1 kilogram mass, this scale would read 9.8 newtons. That means literally the tension in the cable at that point is 9.8 newtons. And that's exactly the right answer. What do pulleys do? Well, pulleys are interesting devices. In this course, we're going to assume that all pulleys are frictionless and massless, just like our strings are massless in this course. What do pulleys do? Pulleys redirect the force without changing its magnitude or size. So in this case, the force of gravity, again, over here, I forgot to put a little F sub g on this one, is going to be 9.8 newtons. Please forgive my horrible arrow. Which means the tension in the rope right above it, to keep that mass stationary, has to be also 9.8 newtons. And the pulley here just redirects it without changing its magnitude. There's no friction, no nothing. So the tension on the other end of this cable against this wall right here has to be 9.8 newtons as well. What's the tension then at that point that's drawn right there? The answer is, as most of you can kind of figure already, is still 9.8 newtons. So at this point right here, tension's still 9.8 newtons. And now, oh man, this is the one time I really wish I was here, because usually this is a table question and your brain warm-up. What about the situation, this third situation? Well, again, yeah, the force of gravity on both of these is going to be 9.8 newtons. But what's the tension in the point right here? And I need you to think about this one. Is it 0? Because these two over here, you know, the two tensions here, I'm just going to draw them over here without actually writing them. This tension here and this tension here are, you know, acting and, you know, pulling against each other. So the tension in the middle point here has to be, let me put the question mark here so you can sort of see it. What's the tension at this point? Is it 0 because it cancels out? Is it 9.8 because the tension has to be the same throughout the cable? Or is it 19.6 because this time the rope has to hold up 2 masses instead of 1 mass, like in these the first 2 cases? If you want to, and I actually recommend it almost, pause the video, think about it for a brief moment before you go forward on this one. At this point, pause. Welcome back. If you did pause, if you didn't, it's okay too. What's going on here? Well, the tension over in each one of these cases to hold these two things up is 9.8 newtons. What's the tension at this point? Well, the tension's got to be the same throughout the cable. Believe it or not, the tension at this point is still 9.8 newtons. You're like, wait, that can't be right. How can it be the same as, you know, in the previous case? What's going on here is this. Basically, it is the previous case. You know, in this case, you'd say, of course, it's 9.8. But what was happening here? The wall was applying a force backwards here to hold this back. We actually didn't draw that before. Here's the force the wall would have to apply, which would be 9.8 newtons. In this case, what's happening? Instead of the wall, this mass here is providing the 9.8 newtons to hold this string in place. The tension here, still 9.8 newtons. It's still the same as the tension at any single point in the cable. It's a strange idea. It's hard to get your brain wrapped around it, but tension's kind of fun. All right. Moving on. So our fourth and final of the 4 common types of friction, and we'll spend much more time with friction, or forces, is friction. And we'll spend much more time with friction a little bit later in this chapter. Friction always opposes the motion or potential motion of an object. And there's 2 types of friction. Static friction, which we're going to write as F sub S, S for static, is the force of friction between 2 stationary surfaces. So static means stationary. And it has a range. The force of static friction, which we're writing as F sub S, can be equal to 0 all the way up to some maximum value. And you're like, whoa, 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 what in the world is this? Well, the maximum value is equal to the normal force, F sub n, times, this is the Greek letter mu sub s. Mu sub s is the coefficient, oh my goodness, it's going to take me forever just to write this, is the coefficient of static friction. Forgive me as I try to write this as fast as I can. And you might say, whoa, 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 where in the world do you find these? Every single combination of different surfaces has its own coefficient of friction. And there are literally tables of these, and I'll show you one in just a second, where you can find this depending on what surfaces are in contact, or you can find it experimentally. Kinetic friction, F sub k, notice K for kinetic, is the force of friction between two moving surfaces, kinetic meaning motion, and it has only a single value, and it's equal to the coefficient of kinetic friction, mu sub k, times the normal force, F sub n. And so it's much easier to calculate. Once something's sliding against another surface, it just takes this one value. And I won't write the coefficient of kinetic friction because it's going to take me too long to write it, but that's what mu sub k is. You will never have to memorize these mu's. I will always give them to you, or you'll be able to calculate what they are. So take a quick look at these. Here's just some common ones. As I said, there's published tables of these. Here, for example, is steel sliding on, or steel on steel. Here's the coefficient of static friction for steel on steel, 0.74, and the coefficient of kinetic friction for steel sliding on steel is 0.57. Notice that the coefficient of kinetic friction is usually less than the coefficient of static friction. Once you get things sliding, they're usually easier to keep moving. And then there's combinations of every possible thing you can think of. And I love this one. So rubber on concrete dry, this is what tires are against a dry road. Notice that when it gets wet, it very quickly changes to a much lower value, which is why it's hard to stop on a wet road. The slipperiest material we have right now is Teflon. And so Teflon on Teflon is the slipperiest stuff we can make. Interestingly enough, it has almost the same, it has basically the same mu sub k and mu sub s, which is unusual. And you go down this one, real quick, you'll see wax wood on wet snow. Yeah, skis, basically. You can see are very small numbers. Ice on ice, which you think would be very, very slippery. It is. But then here, I want to point this one out, because I always get, this one just amazes me. Synovial joints in humans. And you're like, what? Yeah, these are your elbow joints, your knees. Look at these numbers. Their mu's, or their coefficients of friction, are so much smaller than even the slipperiest stuff we can make. Which means your joints move, and you can try it real quick. Move your elbows, move your knees, or even your wrists. Those move with so little friction, because of the fact that you've got liquid inside of there and cartilage, and they slide against each other much better than anything man-made we can make. So when we place joints in older people, those joints which are coated with Teflon are not nearly as good as our original joints, which are amazing. God designed them incredibly well. So yeah, they're just amazing things. So anyway, sorry, moving on. Oh, why do I have this picture? This is the Handbook of Physics and Chemistry. You'll find copies around. It has an entire chapter of different mu sub s and mu sub k's. My favorite one is leather on horn. I'm not joking. It's one of, actually, I should tell you, it's probably the most boring chapter you could ever possibly read. For example, it has almost an entire page of steel on steel. Steel on steel dry, steel on steel lubricated with linseed oil, steel on steel lubricated with 30-weight oil, steel on steel lubricated with neat oil, steel on steel lubricated with whale oil. And after about a whole paragraph of that, it then does steel on copper, dry, steel on copper, linseed oil, steel on copper, whale oil, sperm whale oil, etc. Every possible thing you can imagine, and then every possible thing you could think of. But you know, my favorite one in there, it does list the mu for leather on horn. And the only practical purpose I could think about this is like a sleigh. You got the reins over the horns of your reindeer. Santa probably needs to know this particular mu, but I can't think of anybody else. But it's in that book, which, yes, we do have a copy here somewhere. So here's some sample problems. This is actually from worksheet 1. The question is, what are the forces acting on these objects? And we assume no friction on each one of these cases unless it's actually said or it's told that we have friction. So in the first case, what do we have? We've got an object sitting on a level floor. What are the forces acting on it? You should have the force of gravity and normal force. And these two should be equal in magnitude. So there's no net force or no residual force left on this object. For an object hanging on a string, we've got force of gravity and the tension acting upward. And again, those two should be equal to each other. And now the tricky one. An object's sliding along a surface with a constant velocity. What are the forces required? Yeah, here's the big idea. Force of gravity, normal force, and every single year I get a student's like, no, you also you need the force over here to keep it moving. Remember what Galileo said? An object at rest or moving at a constant velocity must have no net force acting on it. Is this bottom one required? The answer is not at all. To keep it moving at a constant rate requires no net force. And so believe it or not, what's the force acting on this third case? There is no additional force. Yes, you would need a force to accelerate it initially to cause it to get moving. But after that, if there's no friction, this object will continue to slide forever with no other forces besides the force of gravity and normal force. Think about like an air hockey puck. Almost is like this one. All right. Objects and inclines. How do we deal with this one? Well, what forces are acting on it? The answer is there's a force of gravity acting downward. There's a normal force. And if it's at rest, these two forces, no way this could sum up to zero. So there must be another force acting on it. And the answer is yeah, there's a force of static friction if it's stationary. Remember, it's at rest. So static friction is the type we're dealing with, F sub S. And what's the direction of magnitude? You sort of see it here. And you can solve these mathematically as well. And I think it's on my next slide. Let me double check. Okay. Nope, I don't have it. Let's go ahead and solve this one real quick. Let's say that this is a 10 kilogram mass. And just to make our life a little bit easier, let's say that this angle right here is 30 degrees. Now, a couple quick things on this one. Gravity on this thing is going to be equal to 98 newtons. Now, normally when we're dealing with vectors that are not horizontal or vertical, when we're adding them together, we always break them into components that are horizontal, or we broke them into horizontal and vertical components. For things on ramps, we're not going to do that. We're going to do it a little bit more interestingly. We're going to break them into components that are perpendicular and parallel to the ramp. And you might say, wait, Ms. Clemmer, why are we doing it that way for things on inclines? And by the way, this is only for things on inclines. The normal force is already perpendicular to the ramp. The force of static friction is already parallel to the ramp. And so instead of breaking these into their vertical and horizontal components to add these all together, it's much easier to just take the force of gravity, which is the only vector that's not already perpendicular or parallel, and breaking into its components. Now, you might have to have me prove this to you later, but this angle up here is always going to be equal to the angle down here. This is going to be 30 degrees. And if you want, I'll prove it to you later if you want me to do that. But if that's 30 degrees, we can use our trig functions to figure out the opposite side here, which is going to be 49 newtons. And the adjacent side, oh shoot, I better agree my calculator. I don't trust myself doing the math this morning. So 98 times the cosine of 30 degrees is, all right, 84.9 newtons. I would have actually overestimated that one. Now we have these two components. Instead of using this vector here now, I know that these two vectors would add up to that original one. And believe it or not, now I can actually solve a few things. One of them is the normal force. You're like, wait, how do you know the normal force? Well, this component here, which is the component of gravity that's trying to push this block into the ramp, must be exactly equal to the force that the ramp must exert on this thing to prevent it from going through it. So the normal force must be that 84.9 newtons. That same component of gravity that's trying to force it into the ramp. And now here's the other part. This 49 newtons down here is trying to accelerate this thing down, or this block down the ramp. But because it's at rest, the force of static friction up here must be exactly equal to this component that's acting down the ramp. It must be matching it so that it prevents this block from going down the ramp. And so we can actually figure out all of these components. The sum of these three red vectors must be 0, because we know the sum of the forces must be 0. And in this case, it works out. Believe it or not, these three vectors will add up to 0. How did we solve it? Well, we actually broke this 98 into its components that are perpendicular and parallel. And we knew the perpendicular component was equal to the normal force, and the parallel component must be equal to the force of gravity. And so we could actually solve all these. All right. Take a look at these. These are also in the worksheet. Besides the force of gravity, what forces are acting on these objects? Well, in the first case, we have an object, and these little lines here indicate that it's actually gaining speed. It's accelerating. And again, remember I told you we assume all these situations have no friction unless it's intuitively obvious or it's indicated. What are the forces acting on this first one? Well, besides the force of gravity, there must be a normal force. And if you look at this, the magnitude of this vector, the normal force here should be a little bit smaller than the force of gravity, because remember, it's only equal to this component of the force of gravity that's perpendicular to the ramp, and I didn't draw that very well. And this component here is actually accelerating this object. Those are the only two forces acting on that one. There's no friction, obviously, because it's gaining speed. Now, the second case is a little bit more interesting. This one is not moving, so what are the forces acting on it? It's a lot like our previous problem. There's a normal force and a force of friction acting against it. In this case, it's static friction because it's not sliding. The two surfaces are not moving. What about the bottom case? In this one, if you can't see it, besides the ramp itself, which is this piece of wood here, there's another block of wood that's attached right here. What's that block of wood doing? It's preventing this thing from sliding down. Do we need friction in this case? The answer is not really. The bottom board, this board down here, is going to provide a normal force to prevent it from going through it. And this other block of wood over here is going to provide another normal force. I called it F sub n2, acting this way. So Fn1 for the bottom ramp, Fn2 for the other one. And yeah, that's enough to keep this thing from moving. And the sum of these vectors are equal to 0. The same is true with these three vectors equal to 0. The sum of these two vectors are not 0. There is a net force, which is why it's accelerating. All right. Oh, I actually did some math on this one. Okay. Here's the one I was looking for. I wouldn't have to do the other one. So just real quick, you can use this one as a practice. If you'd like to, you can pause the video in a brief moment to work this one out. Otherwise, I'll show you the answers right after this. Welcome back if you paused it. How do we solve this again? We're going to break the force of gravity into its two components. And I didn't write the numbers on this one. Real quick on this one. 7 times 9.8 gives us the force of gravity, which is going to be 68.6 newtons. If the ramp is inclined at 35 degrees over here, that means this angle here is going to be 35 degrees. And breaking these into two components, and no, I cannot do this one in my head. Taking the force of gravity times the sine of 35, gives us that this component down here is, I'm switching colors, is 39.3 newtons. And the other component is going to be 68.6 times the cosine of 35 degrees, which is 56.2 newtons. Once we have those two, what can we immediately imply? We immediately know what the normal force is and the force of friction. Normal force is going to be 56.2 newtons, and the force of static friction is going to be equal to 39.3 newtons. Why? Because we know it's stationary. The force of friction must be exactly matching that component that's driving it down the ramp. Sorry, I've got my newtons over here and my newtons here. Good. All right. So the big idea, and this is where I'm wrapping things up, the big idea is if the sum of the forces, the net force, that same thing, acting on an object is zero, then the object is not accelerating. And for those of you who know it already, you can write net force like this, sigma F. If you haven't seen sigma before, it means the sum of all the forces. It's a shortcut way of writing this or this. Or sometimes we'll just write it as F sub net. Same idea. Is the sum of all the forces acting on a system. Not accelerating means constant velocity, which can be the special case of v equals 0, meaning the object's at rest. Look at this one real quick. This one's another force diagram. What are the forces acting on this crate? In this case, it's moving at a constant velocity, which means the sum of the forces must be 0. And what are the forces acting on it? In this case, force of gravity. Whoops, I didn't draw it. Force of gravity, obviously. And the force of gravity in this case should be 196 newtons. 20 times 9.8. And yeah, there's a normal force. Now, be careful before you write the normal force in this case. And we'll talk about that in just a second. So here's the force of gravity. I should actually label these. And in addition, if it's moving at a constant speed and the person's pulling on it, how is that possible? There must be a force of friction acting backwards. And what kind of friction are we dealing with this time? Well, because the box is sliding on the ground, it would actually be kinetic friction. Now, before we solve this one, we know that the sum of all these vectors must be 0 because it's moving at constant speed. But how do we add these vectors? Well, if you remember, for normal vectors, we break things into their vertical and horizontal components. We're not dealing with something on a ramp this time, so we're not breaking it into perpendicular and parallel components to the ramp because we have no ramp. If you do this real quick, this side, if you remember your 30, 60, 90s, is going to be 100 newtons. And this other side, I'm going to do it really quick in my head because I don't want to stall us, about 173 newtons. What does that mean? Well, immediately then, once you have those, you know what the force of kinetic friction is. It must be 173 newtons. It's the only other horizontal force, so it must be equal to this. And now we can answer the normal force. And here's where it gets a little interesting. You can't, that's not 106, that's 100. The force that the person's applying is actually lifting the crate off the ground with a force of 100 newtons. What does that mean? It means the floor doesn't have to hold up the entire weight of this crate. It only needs to apply 96 newtons to hold this thing up. You're like, what? Wait, what's going on? Yeah, this 100 Newton component along with this 96 newtons is equal to the 196 force of gravity. So in this case, the floor doesn't have to hold up the entire weight to keep this thing or keep it from going through it. And so these would be the forces acting on this thing. How do we know it? We knew that because it's moving at constant velocity, the net force had to be 0. So all the horizontal vectors have to add up to 0, and all the vertical components have to add up to 0. So this 100 plus this 96 has to equal this negative 196 there. Good. All right. One or two last problems. What are the forces acting on this thing? The answer is the force of gravity, obviously, and then we have the two tensions. Are the two tensions equal? The answer is not at all. But what do we know? This thing's stationary, so we know the sum of the forces must be 0. And if you break this up, forgive that little blotch there, my computer is slowing down. What do we know has to be true here? Well, these two components of T1 plus T2 plus the force of gravity must add up to 0. And you might say, well, wait, Ms. Clomber, we don't know T1 or T2. Do we have to do simultaneous equations? You could, but it's not needed in this case. Let me show you why. The only other vertical vector we have is this force of gravity acting downward. This is the only other vertical component over here. This also must be 98 newtons. Why? This must equal this. It's the only other vertical component we have. And because this angle up here is 45 degrees and opposite interior angles have to be 45 degrees, you could either use trig at this point, or you can just use the property of 45, 45, 90 triangles. If this leg's 98 newtons, guess what? This leg over here has to be 98 newtons. And you could prove that with trig if you wanted to real quick. The moment you know this leg is 98 newtons, you can actually immediately figure out that T2 over here must also be 98 newtons. Why? To sort of balance or counteract that. This piece here must be exactly equal to this piece here. The sum of all the horizontal forces must add up to 0. You're like, Ms. Clomber, okay, good. So we got that. So what is T2? Well, or sorry, what's T1? Well, T1, if you remember your properties of 45, 45, 90s, is going to be 98 root 2 newtons, which I'm going to be lazy and leave in the radical form. But if you're curious, I got to quick grab the calculator. 98 times root 2 is 139 newtons, if you really want to write it that way. What's happening here, though? All the forces must add up to 0. And it turns out once you realize that this vertical component here must equal the force of gravity, you could very quickly solve it. And here is the last problem of the day. Oops, oh, actually put numbers on here. Dang it. Okay, sorry. What about this one? And you're like, oh, okay, Ms. Clomber, we do it the same way. We've got the force of gravity and we've got the two tensions. The trick on this one is this. Both of these vectors have vertical components, and both of them have horizontal components. What do we know must be true? Well, the sum of these two vertical components must equal 98. But are they equal this time? Well, you might infer, because the different angles here, these two tensions are not going to be the same. Besides the fact that I number them T1 and T2 to indicate they're different, yeah, they're not the same this time. You're like, well, wait, how can we actually solve this thing? Well, it gets a little bit more exciting this time. This angle down here is going to be 45 degrees, opposite interior angles again. And this angle down here is going to be 30 degrees. And if you do a little bit of trig, you can write this. This side is going to be T1 times the sine of 45. This side is going to be T1 times the cosine of 45. T1's my hypotenuse. And then the other side over here, I can write this. T2 is the hypotenuse, so this side is going to be T2 times the sine of 30. And this side, T2 times the cosine of 30. What do we know must be true in this case? Well, we know the sum of these two vertical parts must equal 98. So T1 sine 45 plus T2 sine 30 has to equal 98. And what do we know has to be true about these two horizontal pieces? They must be equal to each other, and they must add up to 0. A shorter way of writing that would simply be to write them this way. At this point, we have two equations with two unknowns. You're like, no, Mr. Clomber, a system of equations? Yeah. How do you solve these two? You can solve one for either T1 or T2. I was just doing this bottom one. And then plugging it into the top equation for the variable you solved. And you can solve T1 and T2. Yes, I would convert sine and cosines into their decimal equivalents just to make your life a little bit easier instead of leaving them that way. And you can solve this. And if you do, you should end up with, oh, I don't have the answers on this one. No. Um, I'll show you the answers next time. Your homework tonight is involving worksheets and things on ramps. I don't, oh yeah, here it is. Um, and shoot, oh, all right, I'm not quite done yet. I want to quick show you this. Um, the previous equation, I thought I had the answers on the sheet. I did not. Write an equation which describes the forces that act in the horizontal direction. Well, if you broke T1 into its vertical and horizontal components, this side over here would be equal to T1 times the sine of 25. And so, and this side here would be equal to T1 times the cosine of 25. Forgive my handwriting. And then you've got the force of gravity on this object. What must be true in this case? Well, in the horizontal direction, T1 times the sine of 25, this piece over here, must be equal to what? Well, it's got to be equal to T2, the only other horizontal piece. And what must be true about the vertical parts? T1 times the cosine of 25 degrees must be equal to the force of gravity. And then down here, suppose T1 is 50 newtons, determine the magnitude of T2. Well, just using our top equation here, we could very quickly figure it out. If T1 is 50, T1 times the sine of 25 degrees, using our top equation, must be equal to T2. And I'll let you solve that. And if that's true, then what's the mass of our box? You might say, wait, I can't solve this one. Well, we know that T1, which is 50, times the cosine of 25 is equal to the force of gravity. So what you can do on this one very quickly is find the force of gravity. And then how do you go from the force of gravity back to mass? Well, once you know the force of gravity, you know the force of gravity is equal to mass times gravity. So just dividing the force of gravity by g will give you the mass, and you can solve that one. All right. Real quick on this one, draw a force diagram. And when I'm talking about the x direction and y direction here, I'm talking about x is along the ramp. That's our x direction. And y is perpendicular to the ramp when we're talking about ramps. So in this case, what are the forces acting on it? Force of gravity. I'm going to go thin vectors here real quick just to speed things up and make it a little bit cleaner. And then the normal force this way. And we're told that this block is motionless on the ramp, which means there has to be a force of friction, static friction, acting upward against the potential slide. Equation describes the forces that act in the direction. Here, again, just a real quick note, we're told that the angle here is 20 degrees. If we break this into its components that are perpendicular and parallel to the ramp, this side over here, this angle here is going to be 20 degrees. So in the x direction along the ramp, what must be true? This component here, which is going to be FG times the sine of 20 degrees, of 20 degrees, this piece right here we're talking about, must be equal to the force of static friction. This is the component that's trying to push it down the ramp. It has to be equal to that. And then this component here has to equal the normal force. So what can we write? That side is equal to Fg times the cosine of 20. And that has to equal the normal force. And then finally, tell us if the mass of the box is 8 kilograms, determine the value of the normal force. Well, 8 times 9.8 is going to be our force of gravity, which is going to be really quickly in my head. I hope I'm doing this right. 78.4 times the cosine of 20 degrees is going to be equal to the normal force. And so you can solve these. And yeah, I'm not going to do the math. You can very quickly run that through. And you should be good now for the worksheets tonight. Good luck. You've got the rest of the period to work on these. I'll see you next week. Good luck, everybody. Have a great night.